Okay, so good morning, everyone. As Francois introduced, I'm a postdoc in his group, in the Industrial Process and Energy Systems Engineering group located in Sion. And I will be co-lecturing with Francois this course. So today is the only day that you have actually 3 hours of lectures. From next week, as I'll discuss later, you will have also 1 hour of exercise. So this lecture is the only long one. You will not have 3 hours every time. What we're trying to do with this course is that we'll try to make it a bit more interactive. We would like you to participate in this course. So for that, you might have seen the message I posted on Moodle. If you haven't anyway, you can go on the website that's indicated there, responseware.eu, and enter ME-409 EC as your session ID. So in that way, you will be able to have some interactive polls. Just to precise, all of that is not for evaluation, is anonymous, so we don't have any information about yourself and your personal data. It's in complete anonymous form. So the goal of this lecture, which I propose to do in two parts, so I'll stop around 11:15, 11:20 for 10 minutes, and then, 12:15, 12:20 for 10 minutes, and then finish the last half an hour so that we can finish at 1, is to describe what is an energy system. So, first of all, I would like to start by asking you, if you hear the terminology energy system, and maybe we can use the Blackboard for that. So, what do you think is inside an energy system? What are the components that are inside an energy system? Just try to guess for like 2-3 minutes what you think is inside. Don't be shy. Generation of? Generation of energy.
Yes, so I mean like the generation, distribution, transmission, all these things.
Okay. So let's write. I'll write down some items in a particular order on the Blackboard, and then you'll see why I'm putting them in this order. Then, what do you need, for example?
Resources.
Resources. Okay.
Storage. Conversion system.
Conversion system. What do you mean by conversion system?
Something that converts the resource in the energy.
Okay, so to produce something useful for the needs. Okay.
Storage.
Storage. We miss surely one big part here, no?
Waste.
Waste, yes. Put it on this side. When you think of waste, what do you have in mind?
Or emissions also.
Okay. So you're thinking more about waste of a chimney of a plant in this case. Okay.
The receiver, you could produce mechanical energy or electricity. So if you have electricity, there is alternator and equalizer.
Okay, so it probably goes into this area, no?
Yeah.
Or in what does it differentiate?
There's a part of the energy system that has to transmit the energy to use.
Okay, maybe we can write transmissions here. Okay, there's at least one big thing we're missing so far, right?
Consumption.
Consumption. Yes. So. Okay, let's take a number 1 or 2.
the distribution of energy.
Okay, then we have it here. Okay, when you think about, let's say, when you think about energy, what form of energy are you thinking about in this case?
Electricity. Electricity.
Electricity, okay. Is it the only one you can think of?
No.
Heat?
Mechanical?
Yes. Okay, so if you don't have any, do you have anyone else? Or? Okay, so that's exactly the picture I made here, and I put the things in three particular orders. Is because these more or less represent the structure of what I'm gonna talk about in this presentation. So the idea is to show you, to give you an overall introduction to what is an energy system, and you'll see that often it is not that clear what we refer to when we talk about an energy system, and then refer to the three main components of the energy system. So, as you said, on the left-hand side, you say there are the resources. The second element will be the energy demand, and then there will be the main focus of the course, which will be the energy conversion part. So how we take the resources and convert them into useful needs. And then I'll show you, I give a brief introduction to the project you'll do in the course, which will then be presented in 2 weeks, but I'll just introduce you the fact that you're gonna apply the knowledge that you'll acquire during the course by step building up the energy system using a model that we developed in our lab. So, the other day, preparing the lecture, I went in the scientific literature and checked how energy systems are defined. So I went to the different sources, and we don't need to check all these definitions in detail, but by reading them, you can see that all of them are relatively broad, in the sense that if you take, for example, the definition that you find in the Cambridge Dictionary of English, you see that this is defined as a group of things that are used together to produce energy. So this is not a very clear definition of what an energy system is. But there are some common items. For example, in some of the definition, you see that it's not only concerning the technical aspects. As Francois said, when we talk about energy, we cannot forget the economic and social impact. And the main point, which is often forgotten, is that the energy system exists in order to satisfy a given demand, which ultimately is human needs. So you see, for example, the definition is up there, is that energy services are the end for which the energy system provides the means. So ultimately, as we will discuss later in the presentation, what defines the energy system is what we need as final energy services. And there is one thing that I say already now: try to avoid using the terminology production of energy, for example, because as you see in the course, you can only convert energy. So especially in the exam, please do not use the expression production of energy. So some of you mentioned as a first form of electricity, the first form of energy, the main form of energy, electricity. So when often, and that's probably the main message that we would like you to have out of this course, is that when we talk about an energy system, we are not talking, even if the debate is often about only electricity, electricity is not the only thing that is in the energy system. So the first question that I'm asking you, and you can answer using that system, is what do you think is the share of electricity today in the Swiss final energy consumption? So in share, so you have, if you want to change your answer, the system will save only the last answer you give. So we should get at least to 50, I would say, right? So you can keep the application open later. There will be another 3-4 of these questions. Is it? Are you all done? Anyone still has to do it? Okay. So let's try to see if the system works. Okay. So 40% of you is right. 39% of you. In reality, electricity accounts, if you look at the energy flows in Switzerland, electricity today accounts for only 25% roughly of the final energy consumption. So this is a key message that we would like to have in your head. Electricity, when we talk, even if you hear only talking about electricity production in the debate of energy, remember that there is heat and transportation, which actually today, especially in Switzerland, is the main cause of greenhouse gas emission. So here, this is a typical way in which that we use to represent an energy system. It's called a Sankey diagram. It is very useful because it allows you to see the system in one picture. So you see, it's a diagram that needs to be read from left to right. On the left-hand side, you have the energy resources. On the right-hand side, you have the demand, which is divided into the main sectors, which are buildings, industry, services, and transportation. So as you see, this is Switzerland today in 2017. And you see that there is, especially for what is transport, you have still, the system is mostly fuel-based. This is even more evident if you look at another representation of energy system. So this is a diagram that you will get very familiar with the course, because when you will run your model for your project, you will see an output like this. So we can also represent the energy consumption as a country, divided into electricity, heat, and mobility. And if you see, so this is Switzerland in 2011, you see that electricity is around 25% and is mostly produced in Switzerland today by nuclear and hydro. So when we look at the CO2 emission of electricity in Switzerland, they're actually pretty low. But the 75% of the system, it's heating and mobility. And all of this today is basically entirely powered by fossil fuel still. So the emissions, and that's common in many parts of the world, emission of heating and mobility are probably the parts in which the penetration of efficient technologies and low CO2 technology have the bigger role to play. And here you see also with the three components that I mentioned before, and I'm going to discuss now. So that's why I put on the blackboard the organization of things in this structure. So the three main components of an energy system are, first of all, the resources. So we will give a look at what are the fossil and renewable resources that are available in a system. Then we will see what the demand is, and especially the main message there will be to show you that the demand is not something that is given, it's something that depends also on you and the way you use the services that you have available. And then, which we'll talk less about today, but that will be the topic of the next 12 weeks, of course, is the energy conversion technology. So how can we provide the same service with less energy? How can we be efficient in the conversion of energy? So this is a representation that is a quite good representation of what an energy system is. So there are some definitions which will be very important that you remember in the course. And just to make you an example, usually when we look at an energy system from top to bottom, let's take, for example, the example of the heating of a house. We start from our human needs. And our human needs is that we want to be, for example, in that case, we want to cook food. So we need heat in order to cook food. So that's our final energy service that is needed. To produce food, we need heat. And heat, as mobility or other things, is what we define useful energy. So it is the last measurable energy flow that we have in the system before we actually have the energy service. So for example, is the heat that we need for cooking, the heat we need for heating our house, or the mechanical energy that we have at the crankshaft of an automobile, of a car. Only at that point we get to what is called the final energy consumption. So the final energy consumption, in the case of cooking, for example, if you have a gas cooker, is the gas that enters at the consumer's door. So the gas you have at the entrance of your house. So this definition is quite important because, as you'll see, when you look at energy statistics, most of the statistics are in terms of final energy consumption. And this can be misleading because what you should always look at is the lower part first. So look at the end-use service. Because as you'll see before, and that will be the main topic on the of the course, the same useful service can be supplied with different values of final energy consumption. For example, you can have the same amount of mobility provided by a gasoline car or an electric vehicle, but the electric vehicle will be far more efficient. And then you go up to the chain, up to the resources. And the resources normally are expressed in terms of what is called primary energy. So primary energy, said in simple words, let's say, is the energy which is contained inside 1 liter of oil or 1 liter of natural gas at the moment in which you extract it from the well. So these are some definitions that I put there and will be very useful during the rest of the course. So let's look at the resources first. Even if renewables are in general increasing in the world, if you look at the statistics from, for example, the global energy statistics from 2015, the primary energy consumption of the world is still heavily dominated by fossil fuels. Fossil fuels still today account for more than 80% of the global energy consumption. And if you see this, if you look at this graph on the right, which shows the percentage of fuels that are used, this is something that happened only in the last 150, 170 years. In 1850, 95% of the energy needed by humans were supplied by biomass. So basically, combustion of wood in most cases. And you see that this is something that evolved only in the last 170 years, the consumption of fossil, which now have basically the share that we've seen before. And this wouldn't be a problem if there weren't all the consequences related to climate change and global warming that Francois has shown you before in the previous lecture. So if we look at the resources, we can make a quite clear distinction between resources that are renewable and non-renewable, right? So for example, the renewable are indicated here in blue. What does renewable mean? If you think about that, the definition is something that we hear very often, but what does actually renewable mean in terms of a resource? So the main distinction between renewable and non-renewable energies is the difference between the consumption and the generation time. When we talk about a non-renewable energy, the generation time of this resource is much bigger than the consumption time. So all these trees, for example, that were degraded and stored over years to create coal, over hundreds of millions of years, are now consumed by us by burning coal in 50 to 100 years. So this is why the resource is non-renewable. Renewable, instead, means that it's sustainable. It means that our consumption is greater or equal than the generation time. So, for example, the consumption of wood, for example, can be either sustainable or unsustainable, because if today we cut all the wood existing on Earth, it would be a non-renewable thing to do, because next year we won't have wood available. So the sustainability means that we are using this resource at a consumption rate which is on the same order of magnitude of the generation rate. Or in the case of solar or wind, we have a continuous flow from nature that we can harvest. And if you want to make a parallel with banks, for example, you can imagine that non-renewable energy is like money that you have in your bank account and will eventually end as soon as you consume them all. Whereas renewable is like a flow of money, like an income, like a salary you get every month, and you just need to work to harvest it and you will get your money. But again, as Francois mentioned before, the main advantage of fossils is that they are dense. So in 1 liter of gasoline, 1 liter of oil, in 1 cubic meter of natural gas, you have a lot of energy. You see that in this graph, I show you the power density, so the power, the watt per square meter of fossil fuels compared to renewables. And you can see that the scale here on the left-hand side is logarithmic. So the density, the concentration of fossil fuels, of energy in the fossil fuel is much bigger. And that explains why they had such a big success in the past, and also the challenges that we have today to make renewables replace them. So, as Francois mentioned, humanity has remained to the same levels, more or less, of energy consumption for thousands of years. Now, the recent development got us to, it was mainly driven by fossils. If you look at the growth in energy consumption and the growth of fossil and most of the human development indexes, they go together. The problem is that all this has caused climate change. So one thing that we can wonder is that how much still do we have fossil fuels? So how long can we go on with this rate of consumption? And to do this, we need to introduce a couple of definitions. There was this famous way of classifying fossil resources made in the 1960s by McKelvey. So when we talk about resources, there is a main distinction that we have to do between the reserves and resources. So reserves is usually what is known to be there and is economically exploitable at current economics. So it's something that we know that tomorrow we can go get and it will be profitable to get it. Resource is something that normally we know it's there, it can be possibly recoverable, and then it will become a reserve. But right now it is not economical to do that. So what has happened in history is that gradually resources are always much bigger than reserves, and with time and technological development, resources will gradually become reserves. So now, let's see, for example, how much resources you have. So, let's try to in your opinion, and try to use the same system as before. How long do we, if we keep consuming coal at the current consumption rate, how many years do we still have of coal available? Okay, so everyone has answered, right? So let's try to close the poll. You probably don't need to come to lectures because you already know everything, apparently. So the point is that the answer is that if you look at the world global, so the gray line in the graph there, at current consumption rate, we have about 134 years of coal, which is mostly concentrated today in China and in North America. So coal, we will not run out of coal. That is not the solution of global. So there is in a good book that I read recently, and I recommend you, the conclusion of this author is that there is virtually no chance that resource constraints would provide a break on carbon emission in this century. So the author in this book compares the amount of carbon that we would emit in the business as usual scenario on the right to the amount of resources that we have available. You see that the resources are much bigger than what we have. So, as a former employee of Shell concluded, the Stone Age did not end because we ran out of stones, and in the same way, the oil age will not end because we ran out of oil. So the hope that some people have is that in 20 years we run out of oil, coal, and gas. Is simply not going to happen. By the time that will happen, we will have already compromised the global warming situation of the planet. So that's the bad news. And here I put some more data that you can find in the slides. So these slides I also thought a bit as your lecture material, so I won't go in detail in all of them. This shows you the current assessment of conventional and unconventional resources that you have, and what emerges is that the amount of resources that we have are still pretty large. And in specific, I won't talk today only about uranium, about nuclear. You have a lecture on that in which the resource of uranium will also be discussed. So that's the reason why I'm not mentioning it today. So looking a bit in detail on the resources. So the main resource remains oil. It's interesting to see that, for example, today oil is mostly used for gasoline. In reality, when they started taking the oil, harvesting the oil, they were actually taking only the kerosene out because they needed it for lighting, and gasoline was a byproduct that they were throwing into the river. So this was about 100 years ago. And if we look at the same statistic that I show you for coal, the reserves of oil are a bit smaller. So at the current consumption rates, we have about 50 years of oil available, sorry. But again, don't get misled by this data, because as you saw, the resources are much bigger. So even if the reserve at 50 years is most likely, resources will become reserve over time. So we will have probably still 100 years or so. Actually, if you look in the literature, there is the famous peak debate on oil that I don't mention here because of lack of time. It's basically the forecasts that were made over the years to see where the oil consumption will reach a peak and then will go down. So this peak has been always moved forward. And now the current forecast is that the peak will be reached in 2040, but it might be even pushed forward in the future. So oil, similar to gas, has been formed by anaerobic decay of sediment. So mostly zooplankton, basic elements such as zooplankton, algae, and so on. And by decomposition over millions of years, it has formed a material called kerogen, which is then is now sedimented as in either liquid form, such as oil, or then at lower depth normally in terms of gas. So that's how hydrocarbons are normally believed to be formed, even if there are actually other theories about how this, it is a debate. Even in the last year there is evidence that this is the process that was followed. And if we look at how oil is used in a typical refinery, so oil is normally crude oil, is taken to refineries and converted. As you see today, gasoline is not anymore sent to the rivers. It is mostly, so oil, we mostly use it in order to produce gasoline. And there is also a part that goes into diesel fuels and jet fuels. So these are the percentages that we normally have in a refinery. And as I said before, if you look at the quantities here on the left-hand side, you see that up to now we have consumed only a little part of the oil. Most of the oil available on Earth today is still there. It's just available, for example, in viscous form together with sand, or in shales, so it is more difficult to be recovered. Natural gas has a similar formation. So natural gas is today is mostly methane. It has a similar availability compared to the one of oil. So if we look at current reserves, we still have roughly 50 years availability. The origin is similar, and it is mostly available today, as you see in the graph, in Middle East and in Russia. And an important thing about gas, probably the most important development, has been what Francois was referring to before as shale gas. So in the US and also in Europe, but mostly in the US so far, there has been major investments in developing technologies such as the one represented here, such as fracking and so on, in order to extract natural gas from resources that before were considered unconventional. So this has been a big boom in the US. It has lowered heavily the prices on the market, and this, of course, makes it even more difficult to phase out this kind of technology, this kind of resource. And then we have coal. Coal is probably the resource that at the moment we have more widely available, and unfortunately, it is also the most polluting in terms of human health and global warming potential. So I report some data in the next slides. So the main coal, as Francois showed before, comes from harvesting the energy from the biomass with the photosynthesis in the past, and having sediments over layers with heat and pressure have given origin to different kinds of different kinds of coal. And coal is available in different qualities. So you go for the lowest quality, which is peat, which is very good for whiskey, but not for not for energy production. Yes, I just say energy production, so you see that it's a common mistake. And the highest level of coal is the one that we find at the lower level, so around 3-4 kilometers depth, and is the one which is anthracite, and is the one that has the lowest moisture content and the higher energy value. And here I report, only for your information, what is the current situation in Switzerland. So you see that today importing fossil fuels in Switzerland is still relatively cheap. Natural gas is imported at around 3 cents per kilowatt hour. Coal, which is extracted today at around 1 cent per kilowatt hour, is imported in Switzerland at around 3 cents. So these prices of fossil fuels today that we have on the market are still really, really low. And here I report also, again, for your information, what are the prices that you have in the city of Lausanne. There is one last thing I would like to mention about fossil fuels. So this is an analysis I made last year about forecasts that were made of natural gas prices. Is that when you see the forecast in 20, 30 years of how much the prices will be, there's only one thing that you know about this forecast. And the only thing you know is that this forecast will be wrong. So if you look in the past, these are the forecasts that were made in the 1980s in the US about the prices of natural gas. So each black line is a forecast that was made in different years. For example, the first forecast was made in 85, the second in 86, and so on. So you see that forecasters in the 80s were expecting natural gas prices to go up at the end of let's say during the 80s and the 90s. And instead, the red line shows the real value of natural gas, which actually dropped during those years. Then, during the 90s, people were expecting natural gas prices to increase less and gradually stabilize to the low values that they had at the end of the 80s. And all these forecasts did not forecast the fact that actually gas prices went up again. So here, if you make a calculation, you see that you have an error of 300-400% in the term in prices that you have. And now, if we look at the future, most forecasts will tell us that gas prices will increase. So this is what the blue line is the last forecast I had available when I made this analysis. So they are telling us gas prices will increase. But instead, last year there was a major drop in gas prices. So you have a 30-40% error already at the end of the same year in which the forecast is made. This is just to give you an idea of the fact that when you see this number and you have to make an investment for 20 years, take it with some, let's say, the Latins will say cum grano salis, so with a bit of, give a look at this graph before, let's say. And remember that investments that were made on natural gas generation based on this forecast have caused a lot of problems, in the sense that, for example, in the Netherlands, they installed a lot of gas turbines and combined cycles, and they had to shut them down even without starting the operation, just because the prices were not as expected. So this is an important thing to keep in mind. Fossil fuels are cheap today, but the evolution is really uncertain, and when you make a decision as an engineer, your decision will last for 20, 30, 50 years, so take care of that. So now, this used to be a question, but Francois spoiled it, so this is actually more an exam now. So if you listen carefully to what Francois said before, moving to renewable energies, try to complete that sentence. So if we were to check the solar radiation that we have on Earth in a given amount of time, and the question is how much time, that is enough to fulfill the entire energy demand of the world. Okay, so I saw 2 people leaving, so now 62 should be okay. So let's see, now I expect 100%. Huh? Yeah? Okay. So 77% of the class was listening. So, again, if you look at the potential of renewables, renewables have a huge potential. Here are two different analyses that I took from a colleague of mine. You see that the potential that we have from wind, solar, every year is bigger than all the reserves of fossils that we have. So here is the challenge for engineers, let's say. How can we use more of these resources? Why aren't they exploited so far? So let me close on this part on the renewables, then maybe we make a little break and we finish later. So the first challenge that we have with renewables is energy density. So here, just to make you a comparison, when you are refueling your car, the power that is emitted by the refueling pump is equivalent to the power of the sun at noon that heats 3 football fields. So this is just to give you another magnitude of the density, and we discussed about that already before. The second is intermittence and availability. So the sun, as you know, doesn't shine all the time, it doesn't shine at night. And so we need storage technologies, and we need other things in order to be able to harvest them. And then we have the problem of cost. So as I told you before, fossil fuels today are still very cheap. However, these are the data. I put this slide here. This was the graph that was shown up to last year in this course. So these data were from 2006. So you see that in 2006, if you remember, I told you that coal and gas cost 3 cents per kilowatt hour. At the time, solar was around 20 cents per kilowatt hour at best. So these were the data that we had in the past. But there is a but, in the sense that the prices of renewables are substantially falling. As you see, in the last 7 years, the prices of solar panels have dropped by 5 times. This is only in the 7 years. So solar panels cost today what in most forecasts they were expected to cost in 2035. So this is just to give you an idea of how wrong this forecast can be and how ambitious and also intelligent we have to be in not only looking at these numbers and projections, but looking at the energy efficiency first. And now in Chile and in the United Arab Emirates, solar PV is contracted at 3 cents per kilowatt hour. So we are on the same order of magnitude of oil and coal and so on. And in the Netherlands, wind is sold at 5. So this is just to give you an idea that also the fact that renewables are so crazy expensive, as many people say, and it's also advertised, is not always that true. And then you have challenges in integrating renewables in the grid, because as I said, there's the problem of intermittency, and there's also technical and legal frameworks related to that. So, I still have about half an hour. Do you prefer to have a pause or to finish? I leave it up to you. I don't have a poll for it, so just... So you prefer to finish, I think, no? Yeah. I mean, I'm sure you're enjoying the lecture, but you still prefer to finish. So there is one other. The last item that I want to talk about. The main item is 2 main things: is the energy demand and the energy conversion technologies. So let's look first at the energy demand. And again, we start from the energy service. So how much do you think is the occupancy, average occupancy, of a vehicle, of a car, today in the US? So a car that had normally 4 or 5 seats, how much is the average occupancy of a car today in the United States? Okay. So this one should be easy, I hope. Yes, so that's what. So you're a pessimistic class. So it's most cars travel almost empty. So the average occupancy is 1.54 people per passengers per vehicle. And the thing that can be surprising and also disappointing is that on average, the average occupancy of car is decreasing over time. So in some European countries, if you see, this is a graph which is a bit old, but it's the best I could find for Europe. In the UK, Denmark, and the Netherlands, it used to be, probably due to the increase of wealth of people, it used to be, let's say, the ride sharing used to be more common in the past. So why am I mentioning this? Because when we talk about energy, the first thing we should think about is what we do or what people do in their daily lives, how they use the final energy services they need. So now we are concentrating now on the lower part of the figure. Let's say the energy service, the human needs, and the useful energy. So if you remember what I told before is that everything in the energy system exists in order to supply a final energy service, a final energy demand. So what is the energy services that we need? Well, for example, they are as I said before, we need food, so we need heat for cooking. We need transport of freight, which is usually expressed in ton per kilometer. We need transport of passenger, mobility, which is expressed in passenger per kilometer. So these are the things we need in an energy system. So let's take, for example, the example of mobility. So here, as an exercise, I decompose the energy consumption of mobility in two different ways. So in the first decomposition, I took the total energy, indicated with J of joule, which can be divided as the average joule per kilometer, so the fuel efficiency of the car, the kilometer per capita, so the kilometer each one of us travels every day, and the total population. Another way we can decompose the energy consumption is the second one. So is again the fuel efficiency of cars, so how many joule we consume per kilometer, how many kilometers we run on average per each vehicle which is moving, how many divided by how many passengers there are per vehicle, multiplied by the total number of passengers. So here, in both equations, the nice thing is that only one is the variable, for example, because let's assume that the joule per kilometer is fixed, so our car fleet is fixed, and the number of capita, the population of the country, is fixed, and we cannot change on that, which I think is a reasonable assumption. So if you look at that, looking at these two equations, you see that if you want, the first thing we can do to influence energy demand is to change the way we live, let's say, so that the needs we have. So for example, in the first equation, if you want to reduce the energy consumption, travel less. So which means, for example, let's say that the practice of home working or the effect of renouncing to a trip if it's not really needed, this is the first factor that impacts the energy consumption without any need of investment. And the second one, even if you want to move, you can have a higher number of passengers per vehicle. So this, if you do, for example, ride sharing, BlaBlaCar, carpooling, or so on, this has a direct impact on the energy system as a whole. So if tomorrow we double that 1.54, so every car travels with only 3 passengers, the energy consumption of transport is divided by 2. Even without changing anything else in the energy system. So I'm not talking about electric cars and so on. I'm just talking to every person that goes to work alone to just pass by the house of his colleague. Because actually, in most countries, that 1.54 that I showed before gets very close to 1.1 if you look at the commute to work. So the commute to work is generally something that everyone wants to do alone, apparently. Similarly, we can, for example, again looking at the energy service, we can accept a little bit worse thermal comfort. So what we means is that we do not necessarily in summer need the 16 degrees in our houses. So raising that temperature has the biggest impact on energy consumption. And for example, if we want to impact the consumption of freight transport, we can buy less goods and we can buy them more local. So we can either reduce the total kilograms, the total ton of goods that are transported, or the kilometers they have to travel. So what I want to mention here is that in the course we do not talk about demand, but actually demand is the easiest and the lowest hanging fruit you have to influence the evolution and the consumption of an energy system. And here I just show you that since all these units that I was mentioning, so kilograms per kilometer, passenger per kilometers, thermal comfort, are difficult to compare, very often when we compare energy services, we compare them in terms of useful energy because it is the only thing we can measure in joule. So usually what you do when you compare energy service, you go down to the conversion chain, you get to the last step that you can measure, and you measure services at that point. And that is what is called end-use energy demand or useful energy. So all these definitions are available in the slides. Just make sure that when you study them, you familiarize with this concept. So again, if you think about the heating of a house, do 3 steps. The first one is think of the energy services. So what is the temperature I need to be happy? So the second step is the end-use energy demand. So efficiency at the house level, which is, can I change the windows? Can I increase the thermal insulation? Or can I, for example, install a floor heating system, which is at 35, 40 degrees, instead of a system at 80 degrees? So these are the first action that you can take. And this is what are called demand-side actions that do not forget about them. So as I said again, I think I cannot stress it enough. We will not discuss about these actions in the course because our course will mostly look at the energy conversion part because it's the one where engineers and system engineers have their main role. But do not forget about the energy demand. So only once you have defined the heat demand, the useful energy, then you have to think, how do I supply this energy? And only at that point you decide, should I install one technology or the other? So this is the main message here. And you probably heard about energy efficiency very often. So energy efficiency is a term that in the course you'll hear very often. It basically means delivering the same service with less input energy. And as you see from this, it was defined as the hidden fuel. So it's like oil, gas, and so on. It's just that it's there and we often do not see it. But it is the fuel that you will learn to see during this course, hopefully. And as you see here, in the International Energy Agency made a report some years ago showing all the actions in which energy efficiency can be used. So moving to the last part of the presentation, it's probably still the last or the second to last question. Talking about conversion of energy, what do you think is the average efficiency of a standard diesel car? So how much is the efficiency of the engine of your car? Are you replying? No? Hands okay. Okay, so let's close the poll. Oh, okay, so finally you are wrong. So an engine of a car is on average 16–20% efficient. So the fuel you put in your car is mostly used to produce heat and to heat the atmosphere. It is not used in a conventional car to move the car. And this is what I was talking. This is what we will learn in the course. Energy conversion can make really a difference. Do you know what is the efficiency? There's not a question about this. Do you know what is the normal efficiency of an electric motor? with some losses, let's say. Yeah, it's about the motor itself can be normally around 85% or something like that. So you see that when you're converting energy, so switching from an electric car to an electric car from a diesel car can make a radical difference in the energy consumption of the car. So we can provide the same exact service with 5 times less energy. Then of course, and that's why it's interesting to study the energy conversion, you have to see how you produce that electricity. And then of course you have various options also for that. But just looking at the last conversion, you have a factor of 4 or 5, let's say, if you look at the global system. And that also shows that the answer is not always B to the questions I pose. This can be also A sometimes. And so now let's look, I make one final example to show you why energy conversion is so important. So let's take the example of a house. So we want to provide 100 units of energy to a house. And so the first option that we have, now I show you 6 different options that we have for providing heat to a house. The first option is probably the one you have at home, the most standard option you can have. So you have a boiler supplied by natural gas. Let's say the boiler is 90% efficient. So for 100 units of heat, you need 111 units of natural gas. So this is the first option, and of course it has the problem, it might be relatively cheap at current prices, but it causes also the CO2 emissions, as you know. The second option that you have is that you might replace your gas boiler with a wood boiler. So let's assume by now that the energy efficiency of the boiler is the same, but it's actually normally quite similar. So in this case you consume the same amount of energy, primary energy of the fuel. You have a fuel which is renewable. You might have issues related to local emission, for example, of particulate matters related to wood boiler combustion. The third option is that you can heat your house using electricity. How do you do that? You use an electric heater, which is roughly 100% efficiency. It's basically a resistance that uses electricity. Electricity is produced in a power plant that you'll also study in the course. It's called a combined cycle gas turbine. And in this way, you use, to produce these 100 units of heat, you need 100 units of electricity, which in turn need 159 units of gas. So this, if you do this, you do the worst, probably the worst system you can design. But you might be happy to know that electric heaters are still pretty used in energy systems today. So it will be relevant. In this course, you will, in the next lecture, you'll understand why heating with electricity like this is not so smart. But then, using electricity, you can use a technology which is called a heat pump. A heat pump has an efficiency of 400%, which sounds magic, say it like that, but in reality is because it is a technology that is very efficient, so it allows to use free heat from the environment. And you'll also study this technology during the course. So with a heat pump, you only need 25 units of electricity to do the same exact service. And this means that your global system consumption will be 40. So it is heavily dropped compared to the first option. But then you can also say, well, I could produce this electricity with a solar panel on my roof instead of with the gas cycle. So in this case, you have an efficient and fully renewable system. Then, of course, you have to deal with the problems of solar related to intermittent storage and so on. But you see that you can go down to that. And in the course, you'll study also more, let's say, fancy system, more complicated system, such as, for example, you can use the solar and through electrolysis produce hydrogen that can be run in a cogeneration unit, which is a fuel cell that can produce at the same time heat and electricity. The electricity can power the heat pump, and you can produce the heat that you need. So it's also a very efficient system with the advantage that this system, once you produce the hydrogen can be stored. So for example, you solve the problem of the intermittence of the sun. So the main message here is that for one simple thing, such as heating a house, you have various options. And these options are very different one from the other. They have pros and cons. and there is a factor more than 6 between the most efficient and the less efficient. So the system design, which is the focus of the course, can have a huge impact on your on the final consumption, let's say. And the main thing, so here I actually considered only a part of the options. Actually, probably we can list 100 different options that you have for heating a house. And the fact is that you need to consider the entire system. You need to consider heat, electricity, and all the different interactions at the same time. And that's the exercise that we will do various times during the course. So this is the main focus, getting the system view on the energy system, on the problem. So here I have a video that I don't show you, so you can go to lunch earlier, but I recommend you to give a look. It's a nice illustration of what I was just telling you. I just moved to the last slide, which is about your project and what you will do during the course. So in the course, you will be studying the energy system of Switzerland as an example. So as a representative example of any energy system, which is of course some differences, but also many things in common. So as Francois introduced, Switzerland has decided to phase out nuclear power. So here I'm showing you the electricity consumption, the electricity demand and electricity production in Switzerland in today. Actually, this data from 2011, but it's very similar today. So you see that today Switzerland is highly relying on nuclear energy for electricity production. And you see that already today, Switzerland is not autonomous in winter. So in winter, where the dams get, let's say, more and more empty because there's less, because there's snow, and so the water does not flow to the dam, Switzerland is not autonomous already today in winter. So if you remove nuclear, you have a big gap in electricity production. And so this is what has caused the debate in Switzerland. How do we do the energy transition in Switzerland? How do we balance the fact that we won't have nuclear energy available? So the kind of exercise you will be able to do, you will do during the course, is that you will study the entire Swiss energy system, and this will be, you'll have the details in 2 weeks about how this will work. I just show you that what we do in this kind of model is that all the alternatives that I showed you before, and many more, they are all modeled as possible alternatives in the model we will give you. So given a given amount of energy service which is available, which is needed in the system, you will have many different ways of producing it. And the system, the kind of approach that we have to energy system modeling is that we model all the technologies available in Switzerland, all the resources and the demand. And you have a problem in which you have to find the best solution in terms of total cost or in terms of global emissions, in order to find what is the energy strategy that you advise. Actually, in the project, you will play the role of being a consultant for the Swiss government, telling them if the strategy they have decided for Switzerland is good, or if they could do maybe something more. They could have maybe more renewables in their system. So here I just mentioned briefly the approach that we have. Normally, what we look at is the total cost of the system and the environmental impact. So we don't have the time in this lecture to go in detail about how we calculate, for example, the environmental impact. What I want you to know is that when we discuss about environmental impact, we use what is called a life cycle assessment. So we don't consider only the amount of energy and emissions that are generated when the fuel is burned, for example. We also consider what's behind the chain. So how the fuel, for example, is extracted from the earth, how it is converted, and the emissions of disposal and end of life. So part of the system approach is also looking at what is called the life cycle assessment. And there is also a website that you can visit. It's called energyscope.ch. It's a model, a project that we started some years ago in the group of Francois. It's an energy calculator that we made in order to help citizens and politicians to evaluate the cost and emissions of the energy strategy they have. So there you have some variables, and you can play with this calculator in order to design your optimal system. And in the course, you have a model which is similar to this one. Actually, it's not exactly the same version. The one now implemented online is an older version that we have made. But just to tell you, this is the approach you have. So give a look at the website, you find some information, and you also find some answers to some interesting questions that you might have on the energy system. So we got to almost the end. So the main messages that I would like you to take home from this introduction to energy system. So first, energy is not only electricity. So when you have a debate, when you hear a debate about nuclear, for example, it's not only about replacing nuclear, it's also how to use the electricity which is produced by nuclear, for example, for heating, for electric vehicles. So do not forget about heating and mobility, for example. Then we covered the three main components of energy systems: the resources, the energy demand, and the energy conversion technologies. As I told you, especially the demand is something that is very important, that we do not cover in detail in the course, but it's a central aspect of making the system more efficient. About the resources, as I said, it is not by lack of resources that we will get to the energy transition. So we need to phase out fossils due to climate change, and we need to exploit the huge potential of renewables that is today yet not exploited. And actually we need to do it fast, because as Francois said, the amount of events which are linked to climate change are going even faster than expected. And when you think about the demand, always start analyzing the energy service backwards. So start from the energy service and do not take demand as a given. So I have just two slides about the course organization, so some details. So in general, what we will do is that we will have, so we have these 3 hours, and there will be, today was the only exception. We normally do 2 hours of lecture and 1 hour of exercises. Next week, we will start with the lecture. So you start at 10:15 with the lecture for 2 hours, and then we have the exercise hours. From week 3, so let's say from October 8th, we will do the opposite. So we will start with an exercise and then we'll do the lectures. The idea is that at the end of the lecture, we will give you the new exercise. You have 1 week to try and solve it alone. And then you'll come in class at 10 a.m. on the next Monday in order to discuss with the assistant the solution, get help, and ask questions. So we are trying this new format compared to last years, and we will see how it works out. So the idea is that every time you'll be able to have the exercise, try to solve it at home. If you're not able to solve it at home, you can come to class and get help from the assistant to try and solve it. And if you have questions, you'll be able to ask them online. And we will try at the beginning of each lecture, myself or Francois, to cover the part of the exercise, the theoretical part that was not clear. So you see that more or less making some calculation, the course will, it's a 90-hour course officially. So you're expected to work roughly 3-4 hours per week at home or in the library, let's say. As I said, on October 8th, so week 3, we will introduce the project. In the project, what you will have is that you'll be given a model of a Swiss energy system with only few technologies, only the basic ones. And every week, when you will study, when you see a new technology in the course, you'll be able to add it to the Swiss energy system step by step. So what you will have at the end of the course is that you'll see the energy system building up with more and more options. And there is one important thing that you need to do already starting from now, and it needs to be done by October 8th. On Moodle, there is a spreadsheet, a Google Drive spreadsheet, on which you have to form groups for the project. The groups need to be composed by minimum 5 to maximum of 8 people, and we ask you possibly to do it by next week, and they need to be done by week after. So if you have already done it by next week, we can help you also combine into groups. And there will be a report to hand in, which will be 10 days before the exam. The report should not be very long. So if you follow the course and if you have step by step done the tasks that are given for the project, it will not be a very heavy report to write at the end. It's mostly about following step by step the course and doing the tasks that you are recommended to do at each step. So what I don't advise is to do everything at the end, because it will be very confusing. But I'm sure that's not going to happen, right? And the evaluation, so the exam is a written exam. The exam counts for 2/3 of the entire evaluation. It will be exercises similar to what you see in the exercises in class. So once again, if you have done the exercises step by step, and you have understood, you will not find big surprises at the exam. And again, there will be exercises challenging you with this kind of topics. So finding different options, for example, to provide a similar energy service. And 1/3 will be based on the project. And for the exam, yes, so I wanted to see if there was a note here. Yeah, so for the exam, you are allowed, it's a closed book exam. I just mentioned it now because there will be questions then in the future. You are allowed to bring only 15 pages. So let's say 15 pages of personal summary, which should not be a small version of all the printed slides that you have in the course and all the possible exercises. So the idea is that you write down the main notes and the key things that you feel like you need to remember at the exam. We don't want you to learn by heart things. The exercises will be similar to what you have seen, so you'll need the formulas and so on, but that's the thing you'll be allowed to have at the exam. So about the course organization, the lecture will mostly be given by myself and Francois. The two assistants, as Francois said, will be Sian and Louise, so you'll see them here during the exercise hours. About the material, there is no book for the course. The material matches with the slides. We do our best to upload them on Moodle before the lecture. I think, Francois, you uploaded yours at 2, 3 a.m. tonight, no? So we really do our best, but we are redoing the entire material of the course. So there might be cases in which you'll find them right afterwards. We're also recording the lectures, so you'll be able to have the videos online to review the courses. And in the next days, we will set up a platform which is called Speak Up. It will give you the possibility, when you don't understand something, for example, next week the lecture will be on thermodynamics. And if you have questions about the lecture, you can post them there, and people will be able to vote your question. This will give us an idea on which are the topics that you didn't get fully, because we would like you to not lose track during the course. So do not hesitate to come to us and ask questions, and if you don't want to do it in person, you can use this system, and we will try to keep track of that. And just as a curiosity, did you like the experience of having some questions during the lecture, or did you hate me for that? Okay, so we will try to use a bit this system, asking some questions on. Again, it is totally anonymous, you will not be evaluated, and your WhatsApp messages are not recorded by the system. So this is the order of the lectures. We will start from so this one was the first one. We will give you the basics on thermodynamics first and energy conversion cycles, then cover the main fossil technologies, and then focus more on the renewable and the system. And as you see, there will be different lecturers. We will have guest lectures because there are experts at EPFL working on different technologies, so we do our best in order to bring them to the class because we think it can be an added value to hear from them. But what we'll try to do is that to make sure that all the content that you get and the structure of the course will be coherent. So we will have discussions with them in order to organize this. And so if you have questions, otherwise, yes?
Can we do the summary for the exam on computer?
Yes. Yes. Yes, the idea of a summary is that this is usually a big topic. In these 15 pages, you can basically put whatever you want. We wouldn't like to see all the slides and exercises already there. But at the end of the day, even if you do that, it will be confusing because at the exam you won't have 8 hours of time. So the idea is that you study before, you get there, and you put in this summary the things and the formulas that you need to solve the exercise.
I would just add the reason why we add these 15 pages is because in the past I was saying, okay, you can come with what you want, and then the people were coming with what they want. And they were not reading the document before coming to the exam, so they were then trying to read the lecture notes during the exam. So
the exam is not a good time to study. So we had in the past some answers which were saying, when we're asking about the steam cycle, and then they were describing instead the gas cycle because that's the thing they had in the slide. And then at the end they were adding, well, it's basically the same, it's just that it runs on steam. Okay, so this kind of answer is not okay. Also because it's not true, as you see. So if you have other questions?
15 pages or 15 sheets?
15 pages is one A4 per, in fact, per day.
Two-sided or one-sided?
One-sided.
One-sided.